All right, one-to-one and inverse functions are what we're going to be dealing with today. So one-to-one functions are special functions. Let's first remember, what does it take to be a function in has something to do with x values. What did you say? No repeating x values. That's the first rule to being a function. X's don't repeat. Okay. If it's a graph, remember we had the vertical line test to determine that stuff. Been a while. That's chapter 3 stuff we went over way back when. So function, x's can't repeat, and you could use the vertical line test if you had a graph to decide if it was a function or not. A one-to-one function first off, it's a function, so x's don't repeat, but one-to-one means y's don't repeat either. No repeating x's or y's. And it has a test if it's a graph. Not only will it pass the vertical line test because it's a function, but it'll pass the horizontal line test. And horizontal line test works exactly like the vertical line test. It can only intersect it in one spot. If it intersects in more than one, then that's a repeated y value and thus not a one-to-one function. So vertical line test only hits one spot, no matter where you put the line, and it means x's don't repeat, and it is a function. The horizontal line test, it can only intersect in one spot anywhere you place it. If you can place it anywhere and it intersects more than once, that means you have a repeated y value, and it's not a one-to-one function. Okay, so one-to-one functions, no repeating x's, no repeating y's. Regular function, you just can't repeat x's. It's okay for y's to repeat. Okay. Let's look at what an inverse function, or how it even exists. Okay, functions can have inverses, but one-to-one functions have inverse functions. Okay, one-to-one have inverse functions. We can find the inverse of most any function that we're given, but that inverse may not be a function. And the only way to guarantee that the inverse is a function is if the original function was one-to-one. Okay, and what does an inverse function do? Well, inverse functions interchange the domain and range. Interchange the domain and range. Inverse functions interchange the domain and range. Another way of saying that is they swap the x and y values. Okay. So these two statements mean the same, say the same thing. Okay. Interchange the domain and range, you're swapping the x values and the y values out. So on the original function, your domain, on the inverse function, that domain becomes the range. And the range from the original becomes the domain for the inverse. It swaps x and y. That's what you need to know. Okay, it swaps x and y. Okay. Now, so we're gonna go kind of chapter 3 kind of ideas here, kind of similar to the way that we started chapter 3. And we're gonna do these examples where we're deciding is the function one-to-one? So find the inverse. So let's start with this function. So here we have a list of ordered pairs. Could also be graphed if they had these points plotted on a coordinate plane. It's exactly the same idea. Okay, we're just using a list here instead of drawing a graph. So keep in mind that we could be looking at a coordinate plane with these points on it. And I'm telling you it's a function by using function notation, but verify that for me. Is it a function? What are we looking for to make sure it is? No repeating x values. So at -3, -1, 2, and 5, all those are different, so we don't have any repeating x values. So yes, it is a function. Is it one-to-one? Yes. Yeah, we got 6, 7, 13, and -8, all different y values. So there's none that are the same. So that is a one-to-one function. So it's one-to-one. And now for the easy part, the inverse. And the notation we use for inverse, f inverse of x. It's like a little -1 exponent there on the f, or whatever the name of the function is. So f inverse of x is how it's read, but it's like a little -1 exponent on the function name. And what does the inverse do? It swaps what? X and y. So the new ordered pairs are just going to take these x's and y's and swap them. So it'll be 6, -3 for the first one. And the next one will be 7, -1, 13, 2, and -8, 5. And there we have found the inverse function for that one-to-one function. So list of ordered pairs could be a graph with ordered pairs plotted on the coordinate plane, any of those things. But you can determine if it's a one-to-one function. Just are there repeated x's or y's? Either of those are repeated, then it's not a one-to-one function. And then if it is one-to-one, swap the x and the y out of that. All right. What if they do this? They give you f of x is equal to 6x minus 7. What do we know about this function? It's a what? All real numbers. The domain is all real numbers. That's true. The range would also be all real numbers. It's a what? Somebody said it. It's linear, right? And we know it makes a line. We know what does the line look like for this? Yeah, it's kind of going up and to the right because it's got a positive slope. It intersects the y-axis at -7. All those things we know about that linear equation are still here. Is that a one-to-one function? So can we visualize that function in our head, the graph of it? Does it pass the vertical line test? Yes. Does it pass the horizontal line test? Yes, it does. If you can't visualize it, graph the thing, 6x minus 7. You get that graph, and you can look at it there. So don't forget, you got a graphing calculator. That thing can do a lot of things. It'll help you. So definitely can do that. So this is one-to-one. And one of the things we have to remember with equations, and when we graph them, that blue line that was on my graph is just representing a ton of ordered pairs. Okay, it's just an infinite number of ordered pairs. I can't really go and just swap the x's and y's on those ordered pairs because there's too many of them to do. I would never get finished, right? Because there's an infinite number of them. So I could take this equation and find the inverse function of it, just using algebra. Okay, so what I want to do is, what's another way of writing f of x? It really is the same thing as y, right? So that's what the original equation looks like. What does an inverse do? Swaps x and y. So I'm going to swap x and y. Then I'm going to get y by itself again. And that will find me the inverse function. So add 7. One more space here. So if I add 7, that's going to give me x plus 7 is equal to 6y. And now I get y by itself by dividing by 6. I'm going to divide every individual piece by 6. So there's y by itself again. And I have 1/6 x plus 7 over 6. I'm just writing it that way because that's slope-intercept form. You got the slopes more obvious there. If you wrote x over 6, that would be fine with me. Or if you just wrote x plus 7 over 1/6 at the on the bottom, that's fine. But the inverse function notation should be f inverse of x is equal to 1/6 x plus 7 over 6. Again, I would take this or this on a short answer type of thing. Any of those, as long as nothing will simplify. If you had like x plus 8 over 6, then I would definitely want you to split it up and simplify those fractions if you can. So always look for something to simplify. That one, 6 doesn't go into 1, 6 doesn't go into 7, so I'm not able to simplify it all. But if it were something that I could simplify, definitely want to do that. Okay. Well, that's pretty easy. It's linear, right? That's linear stuff's really easy. We've been doing that for a long time. So let's go to something a little more interesting. So here we have a function. And they tell us, what is that x does not equal 1? What's the significance of that? Domain. It's a restriction on the domain. Why is 1 a restriction on the domain? They set the bottom equal to 0, and they told us, okay, well, x can't be 1 because you have that x minus 1 on the denominator out of that. So we want to take this and find the inverse of that. We could graph it to make sure it's 1-to-1 if we wanted to, which I don't think it's a bad idea. Parentheses 2x plus 1 divided by parentheses x minus 1. Guys, you can get your breakfast if you want up here. Just not gonna bother me as long as it doesn't distract you from doing the work you're doing. Okay. All right. So here we have that rational function graph. It would pass the vertical line test, so it's a function. It would also pass the horizontal line test. Remember, there's a horizontal asymptote there at y equals 2. We remember the rules for a horizontal asymptote. The degrees are the same, so you got 2 over 1. So that's how we know that that horizontal line that looks like there might be 2 points that it's hitting doesn't exist because it's an asymptote out of that. So that's kind of makes that a 1-to-1 function. So if it's a 1-to-1 function, that means I can find the inverse of that. So I'm going to do the same steps, but it takes a little bit more brain power to do these steps. It's a little tougher, okay? Because an inverse does what? Swaps x and y. So we got x is equal to 2y plus 1 over y minus 1. So it puts the y in both places that there were x's. And we need to work to get y by itself again. Okay. So how do I even start this problem? Yeah, that's a great idea. If I multiply by y minus 1 on both sides, that'll undo the big fraction, which makes this seem a lot easier. So that's going to be xy minus x. And the other side is just the 2y plus 1. And, well, what do I do now? If I multiply by y, I'm going to create y squareds. Okay, there are 2 places with y in it. Oh. Caleb, well, you got something? If I move the 1 over, that'll get 2y by itself, but it's not all the y's together yet. So that's a good start. What else has a y? The xy. So I need to move it over there too. Move it by subtraction. So we get negative x minus 1 equals 2y minus xy. Now, what Algebra 1 skill can I use to help me isolate y here? Factor what? Why can I factor a y onto the other side? Because it's a greatest common factor, right? Okay, so both got all the y's together, and then I can factor a y out because everybody has one. That gives me y times this. So how do I get y by itself? Divide by that whole parenthesis there. Divided by 2 minus x. And that'd be negative x minus 1 over, I'm going to write it negative x plus 2, just because it's standard procedure to have your variable in the front, right? Now, technically this is correct for the inverse, but I could do a little bit of manipulation on that and not have negatives in front of my x's. If I were to do a little bit of manipulation there and have negative 1 and then x plus 1, and then negative 1 and have x minus 2 there, is this the same as that? What happens to the negative 1s? They cancel out, and I end up with x plus 1 over x minus 2 as the inverse. And I used. Now, in most mathematicians' views, this looks better than the original, or this one right here, because you don't have as many negatives in there. Okay, you got negatives in a different spot, but it doesn't. It's a little cleaner looking. Short answer wise, I'm good with that. But a multiple choice type situation, you may not see that as an answer choice. So you've got to think about, okay, what is an equivalent expression for this? And that may be the answer choice that there is that's the right one. So you've got to think equivalent expressions. So sign changes and things like that are part of that. So that's probably the most difficult part here is knowing, hey, what I got is equivalent to what the right answer is. I just didn't do the simplifying step that they did. So when you're doing practice for this, you're going to run into that as well when you check your answers. So that makes it a little tough. All right. Now, with that, we also have a restriction that we need to tell them about. What's the restriction we need to tell them about? X cannot equal what? 2 on this one. All right. We need to, anytime there's a restriction on that domain, we need to just disclose that. Just like they disclosed it at the beginning. They told us that X couldn't be 1 at there. So that's a good thing to do. All right. Let's do another find the inverse problem. Say we had g of x is equal to x squared. Now, normally, x squared, is it a function or a one-to-one function? Better, it's a function, but is it a one-to-one function? No, it's a parabola, right? So it would fail the horizontal line test. So this restriction that we're going to put on this would make it a one-to-one function. That restriction that I'm going to put on it is that x has to be greater than or equal to 0. And what that does is it only gives us 1/2 of the parabola. So then it passes the horizontal line test and the vertical line test. So that's where that's coming from. They're giving you a restriction so that it will meet the one-to-one rule so that you can find the inverse. Okay, so that restriction, you see a restriction at the beginning, you know you need to have a restriction at the end when you get your inverse out of that. Okay, so let's find the inverse of this. Swap x and y, and then get y by itself. How do I do that? If I take the square root, technically I should be taking the plus or minus square root, right? Because anytime I introduce a square root into a problem, I have to put the plus or minus in there. If it were there to begin with, you just use whatever sign's in front of it. If we put it in there to solve it, we have to do plus or minus. Now that gives us y on the right-hand side, and it's plus or minus the square root of x over there. That seems simple enough, short, quick, and to the point. There's got to be more to it than that. What else is there to this? Okay, so the restriction tells us which part of that to use. Only the positive part. Why only the positive part? It's got to be greater than 0, so that restricts us to the positive side of things. If it said less than or equal to 0, then that restricts us to the negative side of things. So the plus or minus is there, and then we look at a restriction to decide which part of that to use. So we're going to use the positive side of that. So the inverse, g inverse of x, is the positive square root of x. And our restriction again here is x's can only be greater than or equal to 0. Because we know that we're only using the positive side of things. And we also know we can only take square roots of positive numbers there anyway. So that's a restriction on that domain. So not any manipulation, you can do that one. Okay. So keep in mind the restrictions, especially if you have a rational expression or a rational equation or something that has roots in it after you solve it to get y by itself again. So you got to keep those things in mind as you're finding inverses. Overall, the math is not terribly difficult. Example C would probably be the tougher ones where you got to do the factoring and all that stuff. But it's the same process over and over. Okay. All right. Let's talk about how does this even relate to what we did in section 6.1 with the function composition? Because it seems random that we did function composition and now we're doing these inverse things. It doesn't seem like there's a connection. Well, the connection is that you can verify inverses. Verifying inverses. Verifying inverses. If f of x and g of x are inverses or are inverse functions. Semicolon should be a comma. Then f composed with g of x will equal x and g composed with f of x will equal x. Here is the connection. Yes, ma'am.
Well, probably, but on the ACT there was one of these. It was the only one on there, and it didn't even. It was so weird. It was like f composed with g of x, and it had like some another x's, and it didn't have any numbers, and I was so confused. I tried to remember it so I could come back and ask you about it. I cannot remember exactly.
Oh, I remember that one. It was
You're not legally allowed to
equals
disclose information.
x and g of x equals x. So what is it?
F of x equals.
Yeah, that's
Right there on
it.
the front, we're legally not.
Say it again.
G of f of x was x. G of x was x. And then what is f?
Yeah,
I think it was just x.
Okay, that's what I put, but that's weird. That is so weird.
Yeah, I'm glad you brought that. We're on video. I'm glad you brought up a question that was like one that was on ACT, not the exact question. So,
Yeah, we're not supposed to do that.
right. Yeah.
Somebody didn't read the print.
I certify that. Yeah. All right. So, function composition can verify inverses, or if two functions are inverses of one another. So the way we're going to test that, we're going to say we have example E here. Are these inverse functions? Technically, it takes both compositions to prove it. Okay. So if you were going to prove this, like you remember doing proofs in geometry class, if someone asked you to prove if two functions are inverses of one another, you would need to show both compositions in both directions to prove it. Mathematical proof, you have to do both. As far as we're concerned, if it works one way, it's going to work the other way, okay, unless you made a mistake. And that's always a possibility. We're all human. We can all make a sign mistake or miscalculate something. But the idea here is that we're going to show this example. We're going to do both of them. But understand that if you do composition one direction and get you X, and you do it in the other direction, it's going to get you X as well if you didn't make any mistakes. So the second round is kind of the checking spot. Did I do it right? And if you did, then you're going to get X back. If you didn't, you're not. Okay. So here's our functions. F of X, 2X plus 3, and G of X, 1/2 parentheses X minus 3. And, these two are linear, so we'll start with something, fairly simple, but not terribly difficult here. So F composed with G of X. That means we're taking what and putting it into what? G into F. So we're taking the 1/2 parentheses X minus 3 and replacing X in the F of X function. So 2 parentheses 1/2 X minus 3 plus 3. Okay. I'm going to go ahead and multiply 2 times 1/2. Because what's that going to do? It's going to turn into 1, which is a lot easier to distribute than 1/2 is, right? So that's just going to be 1 times X minus 3, which is X minus 3. And then what does -3 and +3 do? Cancels and we get X. Works in that direction. Let's do the other direction. G composed with F of X. That means we're taking what and putting it into what? F into G. So 2X plus 3 is going to replace the X. So it's 1/2 parentheses 2X plus 3 minus 3. Well, order of operations says do the parentheses first. So plus 3 and minus 3 cancel each other out. We get 1/2 times 2X. Half of 2X is 1X. Verified in both directions. So that tells us that F of X and G of X are inverse functions. Now that's an algebraic proof that they're inverses. What does that look like graphically when they're inverses of one another? And that's an interesting thing. So we got a graphing calculator. We're going to use it to help us draw the graph. So I'm going to graph F of X with the blue line. So 2X plus 3, 2X plus 3. And then G of X, I'm going to graph with the red line, and it's 1/2 parentheses X minus 3. Graph. Well, that's uneventful, right? Now here's the cool part. I'm gonna hit Y equals, and on Y3, I'm gonna graph Y equals X. That's slightly more eventful. Because where's that at? Right through the middle of them, right? That if you took this blue and reflected it across the Y equals X line, it would land right on top of the red one. Okay, so inverses. This is linear, so it's not so awesome looking. If you do something that's not linear, it's a little more awesome looking because you got curves and stuff to go with. But the cool thing about inverse functions are that when you do that function composition, what do you get? X. But when you graph inverse functions, what do they reflect across? Y equals X. That same line. Okay, so that's what graphically they'll look like. Now, sometimes when you got rational expressions, those are very difficult to see because you got all those different loops and pieces out of that. It's hard to see that reflection. It's really easy to see the reflection here on linear ones. We notice they're crossing right there on the Y equals X line. All three lines intersect at the same spot. That's usually a clue that, hey, these probably are inverses. So I do my function composition, I should get X when I get done. So that's always a helpful thing. But this would be a graphical verification of inverses. So we got algebraic is function composition. Graphical is it's got to reflect across the y equals x line. That's what we're finding here with these things. Okay. This doesn't get much fancier than that, Jacob.
Well, if that's the case, can we just put the equation in the calculator and see if they're reflecting off the earth instead of working on that?
I want you to prove to me that they do that. So the algebraic part is the proof of that. The graph is the kind of the check to, yeah, that's a kind of a checking spot to say, okay, I should be getting X here. If you don't get X when you do the composition, something went wrong. That's kind of what we're after here is that the graph it's nice and it looks really great, but the actual algebraic composition that showing that work is the actual proof of that. So it's kind of like in geometry. You may know that those two are right triangles, but proving that they are takes several steps. And that the steps in our particular course are that function composition. They are inverses one another. If it's a multiple choice question and they just say, are these inverses, and you do that and it looks like that, then yeah, you can mark it. But if I say, show me that these are inverses one another, I want you to show me that composition. Good question though. Can't dock you for that. Any other questions about those? All right, let's problems that we need to look at for this one. Page 415, 11 through 95. A lot of problems in that set, but a lot of experience to garner with that stuff. So you guys plan out what you're going to do for Pi Day tomorrow, decide who's bringing what and all that stuff, and that's what we'll do tomorrow. I've got some activities that are related to Pi that just be a change of pace.